Okay, welcome back everyone, and we're very happy to have with us Anja Meyer from University of Manchester. And in this last week of the day, she will lead us towards the cohomology as a tools that want to lead.
Thank you very much, and also a warm thank you to the organizers for putting all of this together. So I'm going to share with you today my PhD work. I have very recently submitted my thesis, yay. So now I'm going to tell you what I did. So one would ask why matrix groups and why cohomology of matrix groups. Well, it actually goes back quite a lot. So in his very famous 1972 paper, Phil has looked at the cohomology of GLN over ZP with Q coefficients, where Q is a prime different than P. You might be aware from special representation theory, doing things in dividing characteristic is always a bit more challenging. So it took Aguadé 12 more years to actually move into dividing characteristic, and he computed the cohomology of GL2 over ZP in FP coefficients. And since then, an awful lot of work on the cohomology of matrix group has been done. Of course, lots of stuff on Lie groups, but also very recently, a few years ago, but published only last year, is the cohomology of GL2 over the periodic integers by Diaz, Gabriel, Matze, and Park. And if you recall that the periodic integers are just the inverse limit of z modulo p to the n, in this limit taken over n. One could, of course, ask, why don't we have the cohomologies for all of the groups in the middle yet? So we could just take all the cohomologies of GL2 over z modulo p to the n and construct the inverse limit and arrive at the same result, hopefully. There's just one tiny little bit of a problem. It's hard. First of all, it's z modulo p to the n for n greater than 1. It's not a field anymore. It's a finite ring. And that causes all sorts of problems. For example, I'm not aware how on earth to use classified spaces for this, for example. And I appreciate it's the last talk of the day, so let me split out. There are infinitely many numbers greater than 1. So I was supposed to infinitely many computations. My PhD certainly didn't have the time, and I'm not quite sure if your circulation will either. So let's try to reduce the problem ever so slightly. So what can we do to make it a little bit easier? Well, we can look at SL2. That is a normal subgroup of GL2, so we could put it into a short exact sequence. But this still leaves us with a problem that there are many of these. Another opportunity, possibility could be the subgroups. Earlier this morning, Marcus had told us about the stable elements method. So maybe going via the cohomology of the set of p-subgroups we could get somewhere. But again, it leaves us with this big problem of there are infinitely many of these groups. So rather than continuing to shoot in the dark, we should take a step back and think about what we're actually dealing with here. When I say group cohomology, this is what I have in mind. I fix a pair of G, a finite group, and in my case always FP, and I assign a ring, which is a graded ring. So it consists of infinitely many HIs, such that HI is in the BDU for any degree. And we call the little I is the degree of the cohomology. One very simple example is the cohomology of the cyclic group on p elements with FP coefficients. And this is just given as the exterior algebra on one generator in degree 1 and the symmetric algebra on a second generator in degree 2. This only works for odd primes. For p equal to 2, we have a slightly different one, but it's also very well known. And after the example, the great thing would be to know how to actually compute cohomology. So the way we do this is the Lyndon-Hochschild-Serre sequence. And I'm actually really pleased that Flora May is in the audience, raising after the talk tomorrow, because she has an incredible YouTube channel full of lectures on spectral sequences. So if anybody here is like me and just doesn't understand Bible's textbook, go to her YouTube channel and you find lots and lots of beautiful lectures. The gist of what we're doing is we have something complicated in the middle. So we have a group extension, which is just a fancy speech for we have a short exact sequence of groups. I like that, 2 years in there. And we would like to understand the cohomology of the thing in the middle, which is complicated. And we do it by approximating it from the things on the side. So we have a E2 page, and this just means imagine a book with infinitely many pages in it. And this formula, which I'm going to explain in a second, puts us onto the second page. And then we're going to keep flipping the pages. And at some point, all the entries on our pages are going to stabilize. There will be no change anymore. And this is what we call the E-infinity page. And this is kind of the holy grail which we all want. So what does our E2 page look like? Well, we see that the ij position is given by the ith cohomology of C, the thing on the right, with coefficients. I like when I said I only wrote NFP coefficients because I also wrote in cohomology coefficients, with coefficients in the jth cohomology of A. And together there's a recipe that they convert to the I plus j cohomology of the thing in the middle, or number B. Let's look how this actually, let's have a look how this actually looks like. So just to recall, we have the group extension on the top, and we have a little formula on the top as well. And on the bottom, we see the cohomology of C, the thing on the right. So this is just very straightforward. Once you know the cohomology of the group on the right side, we just put it in. Recall it's a graded ring, so we have infinitely many pieces, and we just chop them there. On the vertical edge, however, if you look at the formula in the very top, if you replace the I with a 0, you see that the 0th column is the 0th cohomology of C with coefficients in the cohomology of A, so the thing on the left. And group cohomology is quite nice, as this is just the invariant thing. So the 0th cohomology, group is always the invariant module of the coefficients under the group action of the group itself. So we just look at the invariant ring of cohomology of A under the group action of C. Because what I have not said earlier, which is quite obvious here now, is we always have a group action of C on the cohomology of A. And then in the middle, we just have certain cohomology groups, which we simply need to compute, but they're just found by the interaction of the different cohomologies of A and C. And I mentioned something about turning pages and finding E-infinity. And here's what we're doing. I'm not particularly comfortable with BMR slides, so I try to keep things as simple as possible. Imagine that there's lots more written on this page. So what we have are so-called differentials, or whether the arrows there. The slope and the length of these differentials heavily depend on the page that we are at. For the E2 page, we go 2 to the right, 1 down. And in order to get from the E2 page to the E3 page, is we take, at each of the points, we take cohomology. Cohomology is the kernel of the incoming, the kernel of the outgoing map over the image of the incoming map. So imagine that we have lots of entries with lots of arrows. So at each position, we take kernel over image, replace our position with this quotient, and are then on our next page. One thing that I would really like to get across for especially those who don't really work with spectral sequences that much, this happens precisely when all the differentials are 0. So we really want all the differentials to be 0. Why? Well, if the kernel of the outgoing map is 0, it's just our position. If the image of the incoming map is 0, we have nothing to mod out, therefore we stabilize. So now that we have a good feeling about what the big tool is that we're about to be using, we're still left with finding a suitable group extension. Preferably one that doesn't leave us with infinitely many computations. So let's try to make friends with our enemy, and we look at reduction modulo P. So we denote by gamma the reduction modulo P going from SR2 over Z modulo P to the N to SR2 over Z modulo P. And this thing has a kernel. And this kernel is the set of all matrices of the form the 2x2 identity matrix plus P times some other 2x2 matrix. And of course, this has to be a subset of SR2. And in particular, this looks like this. And the name we're going to give it is Kn. Now, because this often sparks a little bit of confusion later on, the N always refers to the level. So the N in the Kn always refers to the Z modulo P to the N. So now we have that. Let's see if we can find any information about those. Well, for n equal to 2, the group is actually quite nice. It's elementary abelian and it's isomorphic to Z/3 direct product with itself 3 times. How do we see this? Well, we have 4 positions to put our ZPs. We have the requirement the determinant must be equal to 1, which in our case means that the trace is equal to 2. This gives us a linear restriction, which reduces the numbers of positions from 4 to 3. So we have Z/P to the 3. For n equal to 2, the picture is not quite as nice. There's not much we can say except for they're just not even abelian. So, well, slightly better, right? So let's see what this gives us. We can turn it into a short exact sequence. And there is a short exact sequence. It looks like this. This is not particularly useful. Maybe people with more experience know how to handle it. I don't, because we always have group action of SR2 over ZP on the cohomology of Kn. So of course we know the cohomology of SR2 over finite field, but we also need the group action of this on Kn. But recall Marcus's talk in the morning, Sylow p-subgroups. Let's try this one out. So let S cell P of n denote a Sylow p-subgroup of SR2 over Z to the P to the n. And this is awesome. And why is this awesome? Well, because on the level 1, it's isomorphic to a cyclic group. We know the cohomology of a cyclic group, and we can compute group actions with the cyclic group relatively easily. I mean, easy enough for PhD students at least. So let's try to work with this one, shouldn't we? In order to apply our Lyndon-Hochschild-Serre spectral sequence, we need the cohomologies of the 2 things on the side in order to put them onto the thing in the middle. So we already have the cohomology of cyclic group. So we need the cohomology of Kn. Now, here comes a little bit finite stuff happening. Disclaimer, I only do finite groups, but this thing actually uses the theory of profinite groups. Every finite group can be seen as a profinite group with respect to the constant of the system. So we are on a technical level up to the group. And it can be shown to be a powerful pro-P group. The powerful is the key thing. What it roughly means, I'm not going to bore you with any of the details. What it roughly means is we cannot only go from Z/P to the n to Z/P, we can also go into the intermediate steps. So we can go from SR2 over Z modulo P to the n to SR2 over Z modulo P to the n minus 1. And all these intermediate steps are in fact isomorphic to K2. So even though Kn itself is quite ugly, all the intermediate steps give it this really nice, powerful pro-P group. And I forget my English vocabulary here. Identity. No, never mind. Let's move on. And with a little bit more magic and applying a theorem of Min and Simmons, we can actually find an explicit description. So for those of you who are familiar with group cohomology, this thing is a cohomology of an elementary abelian P group. Why? Well, look at the cohomology of the cyclic group on the top row. So the only difference is we have more variables in the exterior and the symmetric algebra. So finding out that the cohomology of Kn, regardless of which level n we are in, is actually this strikingly simple expression is extremely powerful. Pun slightly intended. So now we can actually work with this. So we need the cohomology of the thing on the left. We need the cohomology of the thing on the right. So we are golden now, right? No, of course not. We still have that. We still have CP acting on the cohomology of Kn. And this has been actually a little bit hairy, to be fair. And to prove it doesn't look that much different than the slide, the line above. But this proof actually took me several iterations to get all the details right. And unfortunately, I've only managed to show it for odd primes so far. So the theorem is that P be an odd prime and be a 3-dimensional CP module. So we come with a group action already. Then the cohomology of Kn is the exterior algebra on this module tensor the symmetric algebra on the dual of this module for any n greater than 1. So here we have the explicitly the group action enclosed, and it means in particular that the group action does not depend on our level n. And this is beautiful because with this, we can set up the E2 page of the spectral sequence for any n that we choose, because it's the same as for n equal to 2. And this is absolutely beautiful. Unfortunately, it does not say anything about convergence of the spectral sequence. It also doesn't say anything about what this group action actually is. So there needs to be a little bit more work to be done. And speaking of, let's see it in action. Now, this is the point where we all should thank the organizers for giving me only 30 minutes, because I had literally no time to spend with all of the technical mess. So thank you to the organizers, I suppose. And speaking of no technical mess, let's continue with technical mess. So we have that C3 can be shown to act on V by permutation, which means that our module V is in fact V3, the indecomposable permutation module of dimension 3. It is self-dualizing. There exists only one of them, so we can say V rather than A. And it comes with our permutation action. So we have the permutation action enclosed both in the symmetric and in the exterior algebra. So, speaking of, we need to put it into our symmetric and into our exterior algebra. The symmetric algebra and the exterior algebras are graded algebras, which means that what we are really interested in order to put it into the body of our spectral sequence is to see how they behave on the module that we feed in, on each and every step. And just one can show with a little bit more technical work that in fact the symmetric and the exterior algebra of on V3 are free for k congruent to 1 and 2 mod 3. This is exciting. Yay! Why is this exciting? Because free means projective. Projective means cohomology vanishes on it. Yes. So this is roughly the picture that we have. In order to keep things simple and not to overload the slide, I have not written down any of the generators. This is the E2 page of the Lyndon-Hochschild-Serre spectral sequence associated to the Sylow group extension at the prime p equal to 3. And the bottom row, with the bottom row stars, obviously, we have the cohomology of C3, which is just exterior, symmetric, exterior asymmetric, double symmetric, and so on and so on and so on. The vertical edge is the invariance ring of the cohomology of Kn under the permutation action. This is taking a little bit of work, and by a little bit of work, I mean a lot. And in the end, I had to dig into the theory of Macaulay modules, which is somewhere you don't really want to go in, but it works. We got generators, and the main reason why I decided to give you this simplified version is the invariant ring has 17 generators. And I was in no mood to type people out. And then we look into the body of the spectral sequence, and we see that only every third row is non-zero. Which is great because it makes things much easier. I mean, not much easier, but it makes it look neater, and it gives us a little bit of an edge. No pun intended here. It gives a little bit of an edge towards the convergence. Because after we set this A2 page up, we would like to know the actual cohomology of the centipede group. I've advertised the Lyndon-Hochschild-Serre spectral sequence as being a computational tool to find the cohomology of a complicated group by embedding it into a short exact sequence and approximating it by the things on the sides. So I think I need to deliver on my promise. And we actually find through some homological algebra that it collapses at the E2 page, which is great, which is exactly what we want, because then we don't have to do too much work. How do we see this? Well, this is the bottom left corner of the spectral sequence. So the arrows indicate it goes on in this direction and it goes on in this direction, which means that any differential coming out of the horizontal edge must be a zero differential, because there's literally nothing there. And because for p equal to 3, our short exact sequence for the Sylow is a split exact sequence, all the differentials into the horizontal edge vanish too. So everything on the horizontal edge survives. Now we go into the vertical edge. And as we see, similar argument as to the horizontal edge, everything coming into the horizontal edge must be the zero differential because there's absolutely nothing where it can come from, so it must be zero. And one can use further arguments from homological algebra to prove that everything coming out of it is also a zero differential. So everything in the invariant ring survives too. So let's deal with a few non-zero entries that we have in the body of the spectral sequence. And because everything in the bottom row survives and everything in the vertical edge survives, the things which are non-zero in the body of the spectral sequence are products of elements from the bottom with the vertical. And because they're products of things that survive, they too survive. So we can apply our beloved Leibniz rule on these to show that all the differentials vanish. So we have our E-infinity page, and what we would like now is our cohomology. So there's a theorem that says that you just need to lift the generators. So let's lift the generators, and we arrive at a computational theorem which says let P be an odd prime. Actually, why do I have the odd prime in there? This is a typo. Wait, 3 versions of proof really didn't spot this. So let P equal to 3 and denote by Sylow 3 of n, Sylow 3 is subgroup of SR2 over Z modulo 3 to the n. Then for any n greater than 1, the cohomology is the same. The cohomology does not depend on our level that we are in. And this is a quite impressive result. I mean, not that I did impressive work, but that we have this stability result. This is awesome. And moreover, the generators and the multiplicative generator and the multiplicative structure of the generators are known explicitly. There are 19 generators, which is why I didn't write them down. And the multiplicative structure is fun to find. If anybody's interested, I have my PhD thesis right here. In case you need to scare yourself to wake up in order to, have dinner later, please feel free to come and have a look. But I just thought not to write them down. So this was the content of my PhD work. And in a way, this is kind of putting the end of something. But if you're considering where we came from, what the underlying project was of where my PhD thesis is set in, this is just the beginning. Because we have 2 avenues to pursue now. First of all, we still have a cohomology of GR2 over Z modulo 3 to the n. So what we need to do first is we need to apply the stable element method to the cohomology of SR2, of the Sylow subgroup of SR2. And this gives us the cohomology of SR2 over Z modulo, hopefully 3 to the n. This is currently work in progress. One hopes that the stable elements do not depend on n either. I am relatively certain they won't, but there is still a little bit of uncertainty because I haven't proven it yet. And as far as I can see, there is a normalizer involved. And considering just how different the structure on a group theoretic perspective, the structure on the n equal to 2 level and n higher than 2 level are, there could still be something going on. So what I mean with this is, in fact, the Sylow 3 subgroup on the level 2 is isomorphic to a Reed product. You can find it as group number 7 in the small library of GAP. And this is only true for n equal to 2, not for any higher n. And because for this stable element method, we need to do a little bit of the group theory as well. So I really hope it's not going to make a difference because the normalizer has the same shape across all levels, but I haven't really proven it, and there's still a little bit of possibility for a hiccup. I hope there won't any, because then we can feed this hopefully just one result into this short exact sequence. The group on the right side is going to be cyclic as well, which we know the homology, and then hopefully it should be relatively simple to find the homology of GL2 over Z modulo 3 to the n. And then we can hopefully construct the inverse limit and compare our result with the result of and Park. And the next far bigger thing is to actually move away from p equal to 3. This is going to happen in 2 steps, hopefully, because during a PhD study, I have found some indicators that we might be able to treat higher primes as one class. They are only indicators. It's not even strong enough for conjecture yet, but this is definitely something I really want to evaluate. I really want to see if we can treat all the higher primes as one class. One of the arguments in favor for this idea, for example, is that this the group that I mentioned earlier, and Park, who did the cohomology of GL2 over the PRX, they have one result for p equal to 3 and one result for any other higher primes, and no result for p equal to 2. So, of course, there could be something. There could be that something gets lost by taking the inverse limit. But I have also found some indicators in the representation theory that could potentially support a conjecture centering about the idea that we can treat higher primes from class. The big headache is going to be p equal to 2. I probably don't need to tell anybody here that representation theory of p equal to 2 is hard, that invariant theory at p equal to 2 is hard, and to make things even more fun, remember this big theorem I was so excited about, my first big theorem that I showed on the slides, which said that the group action of CP on the cohomology of Kn is the same for all n. The result, the main result which I have used to prove this theorem, doesn't exist for p equal to 2. I am quite sure it should work out. I think the reason why those authors didn't do the p equal to 2 case was it's just really fiddly and you have to take different cohomologies into consideration because the cohomology for CP also is different for p equal to 2. So I really hope that I'll be able to generalize this result for all primes and then just have a one long, happy computation ahead of me. And with this, let's have dinner.
Questions?
On your last page, it looks like you somehow got from the Sylow group back to full superposition.
Yes, so once we have the cohomology of the Sylow, which we have at p equal to 3, we can find the stable elements, and then this gives us the cohomology of SR2 over the continuous 3 to the end. And then once we have the cohomology of SR2, which was also the title of my talk, then we can feed it into this short exact sequence to get the cohomology of GR2. But what I'm working on right now is currently trying to apply the stable element methods to explicitly find them, because they are going to give the cohomology of SR2 over the continuous 3 to the end.
Are you actually going to look at the full stable elements theorem, or going to look at some subgroups that control them?
So that is a very, very good question. I think what we need to do is we need to look at the normalizer of the Sylow inside, and then find the invariance under the normalizer. But this theorem only works for abelian Sylows, which we don't have. So there is some other noise term. So you have a diagram in front of your eyes, with which we can define the stable subgroups, the stable elements. So if you take the 2 legs, these should be equivalent to Kn on each side. So Kn. So hopefully we just need to restrict something down to Kn, and hopefully they are then our additional stable elements, which are not covered by the theorem, which only applies for the abelian subgroups. So invite me for a talk in half a year's time, and then we see if I have any progress to show.
So you said you have an isomorphism between the n set and the n is equal to 2. So is this induced by inflation?
No,
Oh,
absolutely not.
so inflation is not an isomorphism, but nevertheless.
It's not induced by that at all. What we actually need to do is, I don't have any appropriate slide to show this, so I'm just going to say it. So we need to go a little step back. So first of all, we look at, actually, let me open this up so I have something to point at. It's not going to be much elegant, but it's something, right? So the lambda 1 is the first cohomology group. So this is just the home space of Kn into P. So this is kind of how we show it. Because as I said before, we have the intermediate levels.
Yep.
And all these intermediate levels are isomorphic to K2. And because the intermediate levels are normal subgroups of Kn, they are fixed under conjugation. The group action, the action we have via the home space is conjugation, so that's fine. In order to move on to the S part, and this is actually a trick that my supervisor told me, which is really neat. So we put a new spectral sequence, so we take a new loop extension where the Kn is in the bottom row. And then we evaluate the differential that comes from the relative edge into the second homology group of Kn. And in the end, the argument goes that we have 3 subspaces of the second homology group. But we only have space for 2 of them. So the image of this differential must be equivalent to 1 of the subspaces. And we show that this image is then isomorphic to the symmetric part. So the group action descends from the homology of Kn in terms of the level to the second homology of Kn.
Any more questions? If that's not the case, then let's move the speaker again.